This app helps to understand the correlation, which is kind of normalized covariance, right? You can see this plot, which is identical to the plot that you have seen in the previous app, if you had a chance to look at it. And you can see that we have a kind of linear trend between X and Y. The gray points are population points, the colorized points are points of our sample. Then you can see that most of the points here have red color because they have a positive contribution to the covariance, right? And only one point is negative. Now you can see that the covariance is, this is the covariance for sample. This all statistics are for sample, and these are statistics for population. So you can see the covariance is 150, right? And why is this number? Because that's the units we have, right? So we simply multiply distances in these units and multiply distances in these units. So if you start taking a new sample, you can see that the covariance, look at this number only. It varies quite a lot, and sometimes it's like below 100, sometimes it's much larger than 100. It actually also depends on the noise. If you increase noise, you can see that the variation will be even larger. However, we cannot interpret this number because they have this units, which is unit of X times units of Y. So therefore, what we do, we use correlation instead. And for correlation, we simply take the covariance and then divide to standard deviation of X and standard deviation of Y. That gives us the correlation. You can actually calculate it yourself. So if you, for example, let me just show you here, 109.22, and then divide to standard deviation of X, which is 57, and then times standard deviation of Y, which is 19.41. Then you can see the result will be 657, which is exactly this number. So that's how we compute the correlation. And then you can see this is the correlation for our sample, right? This is the correlation for the population. Then if I start taking a new sample and then another new sample, you can see the correlation varies quite a lot. But we know from the theories that correlation always between -1 and +1, right? And because sample correlation is not the same as the population correlation, you can actually make an inference, right? So you can take a sample correlation and compute the population correlation. However, in this app, we will do the opposite. We will find out how far this value can go from this value. Okay. The problem is that correlation doesn't follow any distribution. What we need to do, we need to make a transformation. So we need to compute Z prime, which is based on Fisher transformation. How we compute that? So that's the equation you see here. So we simply take a correlation and then we compute the Z prime by using this transformation. And then if we do that, and if sample size is larger than 10, and you can see that indeed our sample, in this case it's 10, then the Z prime follows approximately normal distribution. So we can use normal distribution to describe the behavior of the Z prime values. What you see here, it's the Z prime for my sample. It's this vertical line. You can see it's 0.667. And then this distribution, it's normal distribution for all possible Z prime values. If I take many samples, then you can see this is the 95% interval, right? So if I take a new sample, you can see that this line goes back and forth, but in 95% of the time, the idea is the same as in previous apps, right? So in my case, you can see that I took some samples and then you can see that 93% of them, 14 out of 15 were inside, right? So if I repeat this many times, you'll find out that 95% of the time, Z prime value is inside the confidence interval, right? And then what you can do, you can actually use inverse transformation, which is shown here, to compute the correlation, right? So you can see that if we know the normal distribution for Z prime, we can compute distribution for the correlation, which looks like this. And then you can see that again, most of the time, the correlation of my sample will be inside, right? So sometimes it's outside. For example, in this case, you can see that the correlation will vary between a small negative number, you can see this one, to 0.9. Why such a big variation? Because noise is large. You can see the noise is pretty large here. What I can change the noise, and then you can see how it influences the confidence interval, right? So now the confidence interval is much more narrow. So if you have a noise of 4, for example, in this case, you can see a very good linear trend. Then the correlation will vary between 0.75 to 0.98, although the true correlation is 0.933 in this case. I mean the population correlation. So if I start taking many samples, you can see that most of the time, indeed, the sample correlation is in between, right? Then if I switch to Z prime, you can see we still have a normal distribution here. Okay. Another important thing that influence also the how small the confidence interval is the sample size. So the bigger sample size is, the more narrow confidence interval is, right? So let me get back to the 10, and then let me switch to R again, so we can see this distribution for R. If I have 20, you can see it's much more narrow, right? So I can see now the confidence interval is between 0.83 and 97. This is population-based confidence interval. So this is the borders of future samples correlation, right? So if you take a new sample, then if you see if I make it 30, that it's even smaller. So now you can see that if I take a new sample, because sample size is small, you can see most of the time we match this interval. Again, 95% of the time, because that's the way I compute the interval based on 95% confidence level. 95% of the time it will be outside, but the interval itself is very narrow. Okay. So this is how it works for correlation.